I think we can begin. Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Dr. Prabuchandran KJ, and he'll be speaking on novel first-order Bayesian optimization with an application to reinforcement learning. Dr. Prabuchandran KJ is an assistant professor at IIT Dharwad. He completed his PhD from the Department of Computer Science and Automation, IISc, in the area of reinforcement learning. Post his PhD, he worked as a research scientist at IBM Research Labs, India, for a year and a half on change detection algorithms for multivariate compositional data. After that, he pursued his postdoctoral research at IISc Bangalore as an Amazon IISc postdoctoral scholar for a year and a half on multi-agent reinforcement learning and stochastic optimization algorithms. His research lies at the intersection of reinforcement learning, stochastic control and optimization, machine learning, Bayesian optimization, and stochastic approximation algorithms. His research interest also focuses on utilizing techniques from these fields in solving problems arising in applications like wireless sensor networks, traffic signal control, and social networks. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, and for questions, you may ask Dr. Prabuchandran directly. Over to you, Dr. Prabuchandran.
Yeah, thanks a lot for the introduction. So today I'll be talking about novel first-order Bayesian optimization, and this is a joint work with Santosh Penubotula, who is at IBM Research Labs, Chandramuli Kamanchi, who is at Swiggy, and Professor Shala Bhatnagar, who is at CSC IISc. Okay. I request the audience to feel free to interrupt me anytime during the talk, okay, and you can take your doubts, okay, don't have to wait till the end of the talk. All right, so here is the outline of my talk. First, we will see what is black box optimization, and then in order to solve this black box optimization, we are going to utilize what is known as Bayesian optimization or the zeroth order Bayesian optimization. Then if we have additional information in terms of derivatives, how can we solve this problem efficiently is what the first order Bayesian optimization is about. We'll look at some of the limitations of the current work, and I will tell our research contributions. Then finally, we'll look at some of the application of the first order Bayesian optimization to hyperparameter optimization and reinforcement learning. Okay. So what is black box optimization? So here we are trying to maximize a function f whose analytical form is unknown. So what we have is we can query the function at any of its input domain, and we will be able to get what is the function evaluation at that location. So this is what we have. And there are a couple of assumptions with this. That the first thing, as I mentioned, is the analytical form is unknown. The second one is we may not exactly get the function evaluation, but a noisy evaluation of the function. And further, each function evaluation is very expensive. So basically, we have limited number of function evaluation. In those limited function evaluation, we need to determine the maximum of the function. So an example of an expensive function evaluation comes up in machine learning, where we need to select the model. So model selection is an important problem. So in order to design a successful ML solution, what we have are two parameters. One is the model parameter, and the other one is the hyperparameters. So for a fixed hyperparameter, one learns the model parameter, that is called the training of the ML algorithm, and we vary the hyperparameters and find that hyperparameter that gives the best performance. So the performance of hyperparameter is measured in terms of the validation error. And for each of these hyperparameter, we get a function evaluation, and this process is expensive. So in this situation, what kind of solution methodology we can employ? How does one solve this these kind of problems, where one gets only the function evaluations, based on that, we need to determine the maximum of the function. So one could think of a simple solution where let's try to query the domain at random points. And based on that, I'll try to say whichever point which gives the maximum function value is my answer. This is not going to work if you have multiple dimension, and even in simple one dimension, it doesn't work so well. Another is, why don't we use the general stochastic optimization method like gradient methods, etc. There, the problem is you need to design the step sizes cleverly, and you will require a lot of function evaluations. And as the function evaluation is expensive, it's not so easy to utilize these methods. So what is the alternate solution? This is Bayesian optimization is one way to go about solving this black box optimization with less number of function evaluation. Okay, so people have found a lot of applications of BO or Bayesian optimization in tuning these hyperparameters and also optimizing gait in robotics and many other robotics applications. Further, they have also tried utilizing BO in reinforcement learning, RL. So before we go further, I'll just, for most of you who are familiar with Bayesian regression, and it's not same as Bayesian regression. So what is the difference between Bayesian regression and optimization? So typically what we have to do in Bayesian regression is to find an unknown function. So we assume that that function lies with other functions in a bag, and we need to discover that function from that bag as we get more and more information about the function. On the other hand, Bayesian optimization, we do not intend to discover the unknown function. That's not our goal. The goal is to query, implant your queries at those points where your function is most likely to have maxima. That is the difference between BO and BR, Bayesian regression. However, in BO, we will use Bayesian regression as an intermediate step. We'll see where it comes. Okay. So how does BO work? So in BO, what we are trying to find is maximize an unknown function whose function evaluation we can obtain. Now, our first assumption is we'll assume that the function lies with the other functions in a bag. Okay. Now we need to find the maximum of the function by slowly trying to query the function at various locations and going towards the optima of the function. Now, what we do is, based on our function evaluation, we can filter the functions which do not conform to those function evaluations. So we'll throw out those functions. That is what is the filtering process in a crude sense. Whichever function which do not conform to those function evaluation will be just filtered out of the bag. And based on the remaining member functions, we are going to make an estimate of the unknown function F. A simple way is maybe take the average of the rest of the functions which are lying in the bag and then find the maxima of that surrogate function. So this we are going to call it as a surrogate or an utility function. So note that this optimization of maximizing a surrogate is not expensive because we are keeping a model of the function, and that maximization is not really expensive. The querying the true function value is what makes it expensive. Okay. So once we have this surrogate function, the next thing is to just query at the maximum of this surrogate and find and implant the next query at the location suggested by this maxima, and that is iteratively we keep doing this and then find the maximum of the function. So all these things, let's look at through an example. So let's assume this is the unknown function which we want to maximize. Okay, so here at the dotted line in the black dotted line refers to the mean function in the bag. Okay, so there are many functions. Now let's say we queried at 2 points. The red points indicate the queried points, and we have obtained the true function evaluation. Here, let's assume there is no noise in the system, so we get the exact function evaluation. So in those points, so you will look at all those functions which go through the point. Okay, so that is what is given there. So the blue line, the blue curve denotes the upper envelope and lower envelope, denotes the 95% confident interval of that mean function. So if you look at any particular x value, you can imagine that the mean is the black line, and the top blue envelope is the mu plus 95% sigma and mu minus 95% sigma. So that is what we have. So in the bottom, the utility function measures how good are the points in the domain. So how do you find the utility here? So here we are using what is called the UCB, upper confidence bound utility, where we are saying whichever point has the highest mean plus variance, that will be the point which has the highest utility. So if you look at from that perspective, the location at the end 10 at x is equal to 10 seems to have the highest mu plus sigma, and we are going to query the point next at that location. Now, after you query at the third location, our uncertainty about how the function behaves is going to change. So basically, we have filtered a lot of functions out of the bag. Now, these are the set of functions which pass through these points. Okay. Now, then we compute the utility function in the same way. So what do we do here? We are trying to find the maximum of the utility function. So that is located around like 6, around 6. And then we query the function there. So there the uncertainty about the function value is going to become 0. And so we are getting more information about the function. This is where the Bayesian
I think Dr. Prabuchandran lost connection. Give me 2 minutes to check with him.
Hello, can you hear me?
Yes, Dr. Prabuchandran.
Yeah. Did you lose me a bit early?
Yes, I think it's been 2-3 minutes.
Okay, can you just share, make me share my
screen? Yeah, let me do that. Can you try now?
Yeah, let me just, yeah. So, okay, so I hope this part,
your screen is visible. Yeah.
Okay, so maybe this example we started, I assume, right? That part is clear, right? Did we miss here? Any idea?
Maybe you can go one slide before.
Before?
Yeah.
Okay, so from this point onwards, you have been, okay.
Yeah, you can start from there.
Okay, thank you. Fine. So let's look at the working of the Bayesian optimization through an example. So in this example, we need to maximize this function, which is given in the blue curve, right? Now, so let's say we queried the function at 2 locations. Okay, so that is given in the red, marked by red. Now, so those functions which conform to those 2 points will be in our bag, right? Those functions which do not have the function value at those points will not be in our bag. We will throw that function out of our bag. So the blue thing indicates any function which pass through those 2 points is given in the blue shaded blue region. Okay. Now the black dotted thing corresponds to the mean function of that bag. Okay. Now the plot below, the utility is denoting the utility of querying at a particular location. Here, the mean plus variance is taken as the utility. So if you look at it based on that, the point at 10 is one which has the maximum utility. So there we are going to query next. So now we have queried at 3 points, these 3 points. Then our uncertainty about the function is going to change, right? So now at this point, we had queried at 3 locations, and these are the functions which pass through these points, and there is uncertainty at other locations, and the mean function has changed. Now, if you look at the utility, that is coming around 0.6, right? So that is where we get the maximum utility. So we query the function at that.
Dr. Prabuchandran, I think we lost you again. Let me try connecting with him.
Hello.
Yes. Dr.
Yeah.
Prabuchandran,
Okay.
we lost connection.
Exactly. So I don't know. Today it's some frequent. I don't know why the internet is going. I think power outage. Okay. So let me try to share my screen again.
Yes.
Okay. So maybe I will just stop for a minute and see if there are any questions so far. And I'll know, like, I don't know where I missed.
I think you need to go back. You were at the 3rd step.
Oh, okay.
Yeah.
Okay, fine. Yeah. So, all right, great. Okay. Yeah. So what we have been seeing is the uncertainty about a function in some location is going to decrease, and eventually we are going to get better estimation around the regions where we have queried, and slowly we will start querying around points where the function has the maxima. So that's what I was trying to tell. So if you look at this after 8 steps, we would have almost located the point of maxima, but those points to the left of 2 will no more be selected anymore. Even though there are uncertainty in those regions, we will not try to discover those like the function around those region anymore, because the utility of those regions are going to be less compared to other regions if you look at it. Okay, so let me pause for a while and see if there are any questions about the functioning of BO, like the working of BO, because there has been a couple of interruptions. Let me see if there are any questions. Okay. All right. So please feel free to unmute yourself and speak up, because yeah, I won't be able to look at the chat window. All right. Yeah. So as I have mentioned, so there are 2 steps in order to perform BO. Whatever we have been doing is also called the zeroth order BO. We'll see why it is the case. So in this case, there are 2 steps. One is the filtering step, and another is the next point equation step. So in the filtering step, we need to keep a bag in which your original function lies with other function. And then we need to filter out based on the function evaluations, right? So this is done using the framework of Gaussian process. And in the next point equation step, what we are trying to do is, based on the learned model of the current learned model of the function, we are trying to come up with an utility function and then maximize that utility function. So that is what is the equation step. So we'll go into each of these steps in detail. Okay. So there are a couple of algorithms for doing this next point equation step. One is called the probability of improvement algorithm, expected improvement. So the heart of the BO is trying to design an equation algorithm and actively decide where to query next. So that is what one has to do effectively in order to reach the maxima quickly. Okay. So let's understand how this filtering step is carried out. So whatever I mentioned is a hard filtering, means we throw out the function which do not confirm it. But because the setting could be noisy, what we need to understand is we will have to have a probability distribution over these functions. So how does one keep a probability distribution over function? That is by using what is called the Gaussian process framework. Okay, so what is a Gaussian process? It's a stochastic process with the property that any finite number of these random variables and the underlying stochastic process has a joint Gaussian distribution. So a Gaussian process is characterized by what is called the mean function and the kernel or the covariance function k. So in essence, Gaussian process defines a distribution over functions. Okay, so if you look at a point x, f of x by the property, it's a Gaussian random variable with some mean mu of x and the variance k of xx. So what is this mean function? Mean function is a mapping from the input space, which we want to optimize, which is our domain, to the real number. Okay, so one can think of mean function to be a constant function. When we start this estimation process, we can assume that it's a constant function mu naught, and we will try to tweak this hyperparameter to the right value. And the other component is the kernel function, which is the product. It's a function from x cross x to r. So what does the kernel function do? It tries to control the amount of correlation between the function values. By choosing appropriate kernel, one will be able to put different probability distribution over function. Suppose you choose the popular squared exponential kernel, then we are trying to put a probability distribution over all differentiable functions. If you choose a polynomial kernel, then we will be able to put a probability distribution over those degree polynomials. So if you choose a linear kernel like x transpose y, then we will have a probability distribution over only linear functions. So based on the choice of your kernel, one will have different probability distribution. Also, one can control these probability distribution through these hyperparameters. So L and sigma f are these parameters. If you change it, the probability distribution is going to change. So typically what one has to do in a Gaussian process is to learn these hyperparameters which fits your data well. So typically these things are learned using either maximum likelihood estimation or Bayesian treatment of these hyperparameters. Now, we have seen that Gaussian process is a framework for modeling the function. Okay, so we are assuming the function is one among the bag with other functions. So basically we have a prior over a set of functions. Now, f of x is one among those functions. Now, when you collect data, the probability distribution over these functions is going to change. That is what is Bayesian about. What is Bayesian about here? Okay. Now, suppose we queried the function at let's say x1 to n. So let's understand what is the prior distribution here. So let's look at the location x1 to n, and we will. So f1 to n are these random variables, which is jointly Gaussian, and whose mean is, for now, let's assume for simplicity, it is 0, and k, the covariance matrix, is given by the k, the kernel function. So if you want to sample multivariate, if you sample a multivariate normal at this location, that will correspond to your prior sample for you. So then what one tries to do is, we try to, is there a question? Yeah. So what we try to do is try to find the best hyperparameters that fit this data, whatever given to us. So that is what we will do next. So in the prior, we have a probability distribution over these function values. In the posterior, based on the knowledge, what we have gained, we are trying to convert this prior distribution to the posterior distribution. So we know that in a Gaussian process, any set, the function values at different points in space or time is jointly Gaussian. So we can write this as f1 to n comma f, which at an unknown location as normal with mean 0 and with the kernel matrix k. So now the kernel will have additional components because you have an unknown parameter, which is given by this vector k and kxx. Okay, so the vector k is telling how far this x1 is from x. So based on this, we are trying to find an estimate of how does the function look at an unknown location. So by Bayes' rule, one can compute this distribution is nothing but a Gaussian distribution with some mean mu1 of x and sigma n of x, the variance. This mu1 can be computed from this k, small k and capital K. And so what we have essentially got is, we had a prior distribution, we converted into a posterior distribution over functions. Just to illustrate this, so initially we are assuming the prior distribution is a constant. Okay, so if we take mu0 is constant, and we are going to take some samples from this joint Gaussian distribution. That is what is given in this green as well as orange line. These are jointly sampled normal random variables. Okay, and once you have some data points, let's say here around 9 data points are taken, then it gives the posterior distribution of the functions. So yeah, as you can see, the uncertainty, the blue region has shrunk based on the known information. So that is how, by fitting a GP, one tries to reduce the uncertainty around the function values. Okay, so this can be extended also to the noisy setting because typically the function evaluations are corrupted by noise, and then you can make a modification to the kernel by adding this additional noisy component, and you can estimate this also as a hyperparameter. So the hyperparameters of the system are the coming out of the kernel, 2 parameters, one coming from the mean function mu, and another is from this noisy noise corrupted, the variance of that noise corrupted observation. So that is the 4th hyperparameter. So these are the 4 hyperparameters one needs to tweak to find the best fit of the hyperparameters for fitting the data. So this is referred to as Gaussian process fitting or filtering in the Gaussian process, or the posterior update step. These are different ways of saying the same thing. But as I told you, the heart of the Bayesian optimization is about coming up with an acquisition function using these posterior distributions. So what we have using an acquisition function is a utility of querying at a point. So how good it is to query at a location, that is given by the utility function. So this we compute by taking the mean of the member functions in our bag plus variance or other methods, which we'll see shortly. Okay. So this essentially helps us where to determine or where to query our objective function next. And this is what guides us to the optima of the function. The main thing which comes with the acquisition function is the exploration exploitation trade-off, which comes in the bandits and other things which you have seen. So what is this exploitation and exploration? So let's suppose you know some detail about the function's behavior around some region. So now if you query around the same location, then that is the exploitation. Rather than that, if there are some unknown locations, unknown regions, if we try to query at those locations, then we have exploration. So the goal is to exploit as much as possible, but without compromising on exploration also, because if you don't explore certain regions, your potential maxima could be lying around there. Okay, so you need to explore at the same time and exploit in a clever way. So that's what this acquisition function aims to do. Okay, so a standard most common used acquisition function is called what is called the expected improvement. So what we are saying is, suppose we have learned the current maxima based on the n query points is f of x plus. Now, how we will give utility to a new point is based on how much on an average it is going to be exceeding the current maxima. So that is what is given as alpha of x. So f of x is a Gaussian random variable. F of x plus is nothing but the current maximum. Now you compute this expectation based on the posterior distribution, and then one can this can be also analytically computed using the standard CDF and PDF of standard normal distributions. And then we will be able to optimize this acquisition function using any optimization procedure, and then get the maximum of this acquisition function, and then query the function at that location. So just to illustrate a couple of other acquisition function, the one is called PI, which is shown in the green. So it is, let's say we are looking at location x3. So it computes what is the probability that it deviates from f of x plus more than, what is the probability of it taking a value more than f of x plus. We know that at any location we have a Gaussian random variable. That is what is given in that bell-shaped curve. So we will compute the area under the curve that gives the probability that that random variable takes a value more than f of x plus, and whichever point has the highest probability, then we are going to say that is the point I want to query next. So this is what is known as the probability of improvement. So in the expected improvement, what we do is, rather than just looking at the probability, which may not be the right thing to do, because then the probability may be high, but the function value, what you will get out of that kind of querying, may not be effective. So we take the expectation of this random variable above this point, f of x plus. So that is when you get the EI, expected improvement acquisition function. In the last case, where in the UCB, we just take the upper envelope, which is the mean plus variance. We look at, that is the utility of a point. So one can utilize either PI, EI, or UCB. There are many more, like KG, knowledge gradient, and many more acquisition function, entropy search, and many things. So one can use one of these acquisition function and decide where to query next. Okay. So in summary, we have seen there are two steps to the Bayesian optimization. One is the filtering step, where we try to filter out things which do not conform to the function evaluation. That we are trying to do it in a soft way using Bayesian way. That is, we try to change the probability of the function based on the data. The prior becomes the posterior. Using this posterior, we try to use construct an utility function based on this posterior knowledge and maximize that utility function. And wherever you query there, then that will include that you will include it in your data, and you can filter the functions better. So this is what we have seen in the zeroth order Bayesian optimization. Okay, so let me just pause for a while and see if there are any questions in the Bayesian optimization, BO or ZOBO. It is called zeroth order Bayesian optimization. Are there any questions? Okay. All right. So typically in zeroth order, I hope I am still connected, right?
Yes, you are.
Okay, great. Okay. So in zeroth order Bayesian optimization, we do not utilize derivative information, even if it is available, right? However, that information could be very useful in performing these optimization more effectively. So that's what first order Bayesian optimization aims. So here, one question is, why does one want to use the gradient or derivatives? As you know that every optimization which utilize the gradient has been shown to work very well compared to its counterpart, which are gradient free, but not in every case it is better, but most of the cases it is seen to work very well in neural networks and many other cases. And also people have used these gradients to and shown that this hyperparameter optimization can be done effectively rather than just using the first order, zeroth order information. So recent work by Wu et al. Has shown that this works for hyperparameter optimization, as well as in shown that it is more effective in a test function as well as in hyperparameter optimization case. Okay, so in the first order Bayesian optimization, the main idea what people aimed at doing was, so if you have a Gaussian process, the derivative of that Gaussian process is also a Gaussian process. So using this fact, we are going to model the problem as a multi-output Gaussian process. That means the query is X, and now we are going to get D plus one outputs, not just single output. Earlier we just had one output. Now we are going to have D additional outputs, all for the partial derivatives. Dou f by dou x1, dou f by dou x2, and dou f by dou xd. Okay. Now, so this can be modeled as a multi-output Gaussian process, and we know that if you have a mean function mu, the mean function of the gradient is also the gradient of that function, and similarly one can compute the kernel of the GP, multi-output GP, using the taking partial derivative with respect to the kernels. And if you want to get a Hessian, you have to take two partial derivatives, and you will obtain the Hessian of that kernel. Okay. So one thing to note here is, earlier we said that the posterior update step requires a matrix inversion, and that is order of n cube. However, in this case, the matrix size has even increased. It is now n into d plus 1 whole cube, because instead of just one output, we have a whole bunch of outputs. So that is one of the pitfall of utilizing FOBO, and that restricts its wider applicability. So one of the crucial fact which the first order Bayesian optimization work missed out was, it didn't use the gradient of a function at maximize 0. That is one of the crucial fact which we will be utilizing in our work. And the second thing is, this order of n into d plus 1 cube is quite costly. So what we do in our work is to think of it as an independent Gaussian process. So these are the two main key contributions of our work, where in the first order Bayesian optimization, they do not use that first order information to design an acquisition function. What they do is only they try to utilize it in the filtering step. So yes, it is true that in the filtering, if you use more information, you will those functions which do not conform to both function as well as the gradient will be thrown out of the bag. That will give us more sharper uncertainty guarantees. However, one important fact in optimization we know is the gradient of a function at the optimized 0, which is something which they have not utilized. As a true spirit of BO is to go for the point where it is maxima, and so that is why we are in our work we constructed a question function that tries to obtain this maxima directly using this fact. So the first assumption we make is, we assume that our Gaussian process, we assume that instead of having a multi-output Gaussian process, we'll assume we have d plus 1 separate Gaussian process. There are twofold advantage. One is the hyperparameter estimation becomes reliable. Second is it reduces the complexity from order of n into d plus 1 whole cube to order of d plus 1 times n cube. So the cube in the dimensions vanishes. Okay, and further, this can be parallelized, and one can build a parallel GP for each of these partial derivatives, and you can utilize this. So that is the first contribution. And the second contribution is, like, they fail to utilize that at a maxima, the gradient is 0. It also comes with other problems, but we'll see how we can avoid it. So using that fact, what we have done is we have designed acquisition functions that tries to look at points where the gradient of the function is 0. So using these, the gradient of the original function and the and also from the partial derivative, the point suggested by that, we are trying to come up with a better search procedure. That's essentially what we have contributed. Okay. So as you can see, each partial derivative, we can look for where the partial derivative is vanishing. And so each partial derivative is going to suggest one point. So there are going to be now d plus 1 points, one suggested by the function GP, and there are d more points suggested by the derivative GP or the gradient GP. So the next thing is we have to combine it, aggregate it, and try to come up with a single point, and we want to query the function at that location. Okay, so that is done, what is called the point aggregation. Note that one important thing is the point where the gradient is 0 need not be just maxima, it could also be minima, it could also be saddle point. So we need to somehow not select such points. So to avoid this, what we do is we try to learn the significance of the point. How do we learn the significance of a point? We take those points suggested by the gradient GPs. Now you put the point in your function GP and compute what its mean function is. So mu1 of xi n plus 1 gives the significance of that point, okay, in the function GP, using the function GP. Now, there are two ways to combine the points. One is by just the convex combination of these d plus 1 points. Other way is pick the points where this significance is maximum. So that is the maximum combination. In another convex combination, we weight each point by its importance, okay, and then we combine it. So these are two straightforward ways or heuristic ways one can combine the points suggested by the gradient GP. So let me give the algorithm now, our algorithm, which is, so let's come back and remember that the goal is to optimize a black box objective function. So for that, what we have done is we have to fit d plus 1 Gaussian process models using the current set of function and gradient evaluations. Then what we do is we calculate and optimize the equation function. Okay, so that is the one which tells for which point the gradient is going to be 0. So each point is going to say suggest a point where the partial derivative is going to vanish. So using that, using also the function GP as well as these d points suggested by the derivative or gradient GPs, we either use a convex combination or a maximum combination to get the next point. Then we can query the objective function at that location, and we repeat this until the convergence is reached or the budget is exhausted. Okay, so let's look at an example. This is an example of an Ackley function, two-dimensional Ackley function, where it has multiple maximas. And now I'll show you the result comparing various algorithms. So in the y-axis here refers to the regret. Regret is log of the value found by our algorithm, the difference between the value found by our algorithm and the true value. Suppose your true value is 100 and the algorithm has been able to reach 10. So 100 minus 10 is 90. We take the logarithm of that. So log of that is what is the regret here. So the one which has less regret seems to perform well. Here CKG refers to our algorithm that uses KG equation in our function GP, and CEI refers to our algorithm which uses a different equation function in our function GP. As you can see, it clearly outperforms the zeroth order methods. So that which means to say that it uses the first order information more effectively compared to the other methods. Here the DKG refers to the existing first order method, which only uses the equation, but which only uses the gradient information in the filtering step and not in the equation step. So it even seems to have outperformed the first order optimization, which models it as a multi-output GP. So this is another example of Hartmann function, where here also, as you can see, the first order methods, our first order method seems to clearly outperform the other zeroth order method, and also perform as good as the existing first order method. Okay, so let me see. So in the rest of the talk, what I would like to do is take some application of this first order method, which we are working on it currently with Utkarsh, who is a BTech student, and Tejas, who is at IIT Hyderabad. So let me pause for a while and see if there are any questions in whatever we have discussed so far. Okay. All right. So what can we do using whatever methods we have? See, typically these BO methods has been known to be very useful in automatic hyperparameter selection. Okay, so what is a hyperparameter? Many of you may be familiar with, but I'll just quickly discuss what it is. So in machine learning, there are two kinds of parameters. One is model parameters, and another is hyperparameters. So in model parameters will refer to the neural network weights and biases and all that. And in hyperparameter, these are the, for example, the number of layers in the neural networks, or the learning rate, and dropout probabilities, and things like this turn out to be hyperparameter. In order to design an effective ML method, what one needs to do is come up with the best set of hyperparameters. Typically, one does this using what is called grid search. So basically, you discretize your different hyperparameters, and you will search for the best hyperparameters in that space. However, that is very time consuming, and since it's multimodal, it may not be straightforward to do that. So typically one will be happy if one has a automatic hyperparameter optimization. So people have tried to use BO in this hyperparameter optimization. So let's look at an example here. Suppose our validation loss is this function, x minus 0.5 square. So this is the function we really want to minimize here. So instead of maximization, so far we have been seeing, right now I'm looking at a minimization problem. So assume that you want to minimize this validation loss, but you do not have this function to minimize. Instead, you have the training. One typically minimizes a training loss, which is given as the function x minus 1 whole square plus this lambda times norm x square. So lambda is the regularization parameter, and one needs to learn. So for lambda equal to 1, one will minimize the validation loss. By trying different lambda values, you will be able to find which is the best set of hyperparameters. So this we try to learn using our Bayesian optimization. So one can compute the gradient using what is called evograd. It's a gradient method for computing gradient using evolutionary algorithm. So here in this example, we don't have to even resort to that. We can compute the gradient with respect to the original function as a function of lambda. So one can do that. Once we have that, then we can employ this first order Bayesian optimization. And clearly, you can see that first order method seems to have better performance over the zeroth order method. So this is just an illustration to show that if you use the first order method, the hyperparameter optimization can be done effectively. So the second example would be to consider the task of training on an MNIST data set. So in this, the goal is to maximize the test accuracy. However, the main caveat is like the validation test images are rotated by 30 degrees. Okay. So, but the training images are not rotated. So if you train on that and test on a validation, your accuracy is going to be poor. So here the hyperparameter for you is the amount of rotation you need to do on your training image, and then based on which you want to maximize the validation accuracy. So here we train the data set using a CNN. Okay. If you don't rotate the image and you simply blindly train it on the training image, that means it corresponds to 0 degree rotation, and then the accuracy, test accuracy is going to be poor. Okay. So what we are trying to do is, because both validation and test images are rotated by 30 degree, so our hyperparameter is to rotate the training images and compute the gradient with respect to this rotation. And using this, we will find what is the best rotation for which we will get the maximum accuracy. So here we used for training this data, MNIST data, we use the linear architecture where you have set of convolution neural networks and then fully connected with ReLU activations. Okay, so you train this for certain epochs, and then you plot the validation loss as a function of iteration. So as you can see here, we tried 5 different runs here, and in the zeroth order optimization, once has found rotation of 21, and at that time its accuracy, test accuracy is very high, but other times its test accuracy quite poor, 85%. But on the other hand, every time the first order method, which it is able to find the right amount of rotation one has to do, because it uses this additional information, and the accuracy is also better in all the cases. Okay, so the summary is like one can perform this hyperparameter optimization automatically using first order methods better compared to just using the zeroth order method. These gradients can be computed using backprop or automatic differentiation package or other existing tools. Once we can do that, it is possible to do this optimization better than in less number of iteration compared to the zeroth order Bayesian optimization. Okay, so and further you can see that so we plotted the regret, basically the validation loss with as a function of iterations. The zeroth order Bayesian update got stuck at almost some non-zero value, but on the other hand, for the first order, it goes to 0 with the number of iterations. So this is another application which I won't get into details. So one question is, how can one get this gradient information? Typically in RL, if you look at policy gradient RL, this gradient information is freely available. So it is not at all computationally difficult to obtain the gradient. So this can be computed using what is called the policy gradient theorem. Okay, so because the gradient is freely available, one can use that and train some RL problem. So if this is just a plot of training an RL, initializing an RL task with different kinds of initialization. If you use a random initialization in a policy gradient algorithm, typically what happens is it takes a lot of episodes to explore, and then finally it reaches the optimal reward. On the other hand, if you use Bayesian optimization to initialize this process, it can quickly come to the correct solution faster. So that is one useful application of utilizing Bayesian optimization in RL task as well. Okay, so there are a couple of future directions what we want to work on, and already working on it, is to come up with effective utility function that can utilize this gradient and utilize this optimization fact, and also utilize these algorithms for RL tasks to get better initializations, and also if possible come up with better RL algorithms. So far whatever we have discussed is using maximum likelihood estimation of the hyperparameters. One can also try using Bayesian treatment, which will be more robust compared to the Bayesian treatment. So the other one more direction is to use different kind of kernel rather than just using exponential kernel based on the problem domain to make this more effective. So with that, I'll end today's talk. If there are any questions, let me know.
Thank you, Dr. Prabuchandran, for an informative talk. We can take a few questions now. Are there any questions? So if there are no questions, then we can end the session here today. Thank you again, Dr. Prabuchandran, for agreeing to speak at the seminar series. And as discussed before, we'd like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you and have a great evening.